The next rule is called the loop rule. And the loop rule is that the sum of the voltage differences about any closed loop, in other words, makes a complete circle, starts and ends at the same place, the total delta V is equal to 0. And this makes perfect sense. If you start and end at the same place, what's the voltage difference from the start to the end if the start and the end are the same place? It's 0. So the sum of the delta V's across all circuit elements in any closed loop has got to add to 0. So what we have here is an analogy for the loop rule that hopefully will make this make plenty of sense. What I've got right here is, let's take a look at this circuit. I've got an EMF right here, E1, and I've got current I going through this single series of components. I've got R1, which is a little bit smaller than R2, and I've got E2, which is smaller than E1. Now, let's take a look at what we can again use height as an analogy for electric potential. It still works. So what I've got here, I'm representing this EMF E1 by an elevator that's going to take these positive charges up to this height right here. So it's increasing the height. I'm just going to label it E1, just like that's an increase in height. And then what happens is these positive charges, which are now up here, they're going to slide down this hill. And this hill has friction. So those positive charges, as they slide down, that gravitational potential energy, which is an analogy for electric potential energy, gets turned into thermal energy because there is friction here. They're going to lose the amount of height, which is the amount of potential loss, is negative. It's negative I, and this is representing R1. Then I have another elevator here, and then they go up to a slightly higher height here, and notice that this is represented by that thing right there, and it's not as much as E1. It's a little bit less. E2 is smaller, and then these charges, once they're here, they again slide down this hill. It's a bit of a steeper hill. It's a bigger change in elevation, and this is going to be negative I. It's the same current because it's one series. This is also I right here. And it's IR2. R2 is bigger. It's a bigger drop right there. So here's the question. And then all these charges end up down here, and they can take a free ride back to there because there's no work required to go along a flat plane. Now, what is the total change in height if you start here, and then you end there as well? Total change in height around a closed loop is equal to 0. Doesn't matter what path you take, no matter how many stairs you go up, how many elevators you go up, how many elevators go down, escalators up, escalators down. If you start and end at the same place, the total change in height is going to be 0. And in the same way, this total change in potential is 0. Now, what we do is, when we're using the loop rule, you can travel around a closed loop in any direction. You do not have to go in the direction of current. You can just pick a direction to walk around, and it's got to be a closed loop, but you can pick any direction to walk around that loop that you want. Now, how we use the rule is that if you're going in the direction of assumed current, delta V's across resistors will be delta V is negative IR. Because through a resistor, if I may draw one right here, if the current is going through this way, these charges are losing energy as they go from there to there. They're losing electric potential energy because some of their electric potential energy is turning into thermal energy. So this end will be high voltage, high V, and this end will be low voltage. If you're traveling in the direction of current, it's going to be a negative change in potential or negative IR. However, if you are walking around in the opposite direction, so in other words, if we're taking our little trip and we're going around this way, you don't have to walk around the direction of current. If we're walking this way, that's the direction of our travel, then we're going to go to higher potential. We're starting where it had already lost a lot of electric potential energy, turned into heat, and we're ending up by traveling this way, that's the travel direction. If you go that way, then we are going to add IR. In other words, delta V will be positive IR if we're going opposite that of assumed current. If you are wrong about your direction of assumed current, again, that's fine. It'll just, your value will come out negative and everything's going to be fine. Now, if you're going across an EMF source, so here's an EMF source right here. And remember that this means the short end is always negative, the high end is always positive. If you are doing your traveling from the negative to positive, if you're traveling this way, that's the direction of travel, then this is like the bottom of the hill, this is the top of the hill. So it'll be, if this is EMF E right here, the delta V from there to there will be positive E. That's the change of potential from there. However, if we're walking around in the opposite direction, if we're traveling this way in our loop, if that's our travel direction, then it will be the opposite of that. It'll be negative E, because if we're starting right here and ending there, it's like going from the top of a hill to the bottom of a hill. Our change of potential is negative. With capacitors, pretty much the same as batteries or EMF sources, i.e. If you're going from the negative to positive plate, you're going up to the top of the hill, so that would look like this. Here's our capacitor, and this is the negative and this is the positive plate. And again, we're traveling around. It all depends on which way we're traveling. If we're traveling around this way, traveling this way, that's our direction of travel, then it'll be going to a higher potential. Bottom of hill, top of hill, we're going plus Q over C. And remember that caps are quite overvalued. That's why the delta V is Q over C. But if you're traveling this way around your loop, then it'll be negative Q over C. We're going to the from top of the hill to the bottom of the hill.